You've probably heard the terms pods, deployments, services. You've seen the kubectl command and those endless YAML files. And let's be honest, it feels complex, abstract, and maybe a little intimidating. But here's the thing, these aren't just buzzwords. They're the tools that answer the questions every developer eventually faces. What happens if my app crashes in the middle of the night? How do I handle a sudden traffic spike? And maybe most importantly, how can I update my code without taking the entire site down? We are going to answer those questions. We're going to demystify Kubernetes by building, scaling, and updating a very, very simple application. The Joke app. Seriously, it's a tiny web server whose only job is to tell you a bad joke. And it's the perfect way to make Kubernetes concrete. So here's my promise to you. In the next 30 minutes, you will take a single Python file and transform it into a robust, self-healing, and scalable service. We won't just talk about theory. We will solve real problems, one kubectl apply at a time. You are going to master this table. We'll cover everything from what pods and deployments actually are to how they give you powerful features like self-healing and zero-downtime rolling updates. This is your roadmap, because Kubernetes isn't magic. It's a powerful system for maintaining a desired state, and you will have the skills to define and manage that state yourself. Let's get started.
Our journey starts here, with a ridiculously simple application I call the Joke app. Its only job is to tell you a random joke. That's it. It's not going to change the world, but it's the perfect way to learn this stuff. And I want you to build this with me. Go ahead and create a folder called joke-app, and inside that folder, create one single file called app.py. Okay, here is the application code for app.py. It's pretty straightforward. We import a few libraries, Random, Socket, and Flask, which is a tiny web framework. We create our Flask app, and then we have this. A simple list of completely neutral jokes. What has an eye but cannot see? A needle. You get the idea. Down here, we have a single function, tell a joke, which runs whenever someone visits our app. It just picks a random joke from that list, gets the computer's hostname, and then returns both of them as a string. Finally, this last part simply tells the app to run on our machine on port 8080. Got it? Good. Now run it from your terminal. Just type python app.py. And in a second terminal, let's test it. Type curl http://localhost:8080. You should see something just like this. A joke. What gets wet while drying? A towel. Followed by a second line, served by my laptop, or whatever your computer's name is. It works. So, are we done? Not even close. This brings us to the core problem, the most dangerous phrase in all of software development. It works on my machine. Right now, we have three huge problems. 1, inconsistent environments. Sure, it works on your machine, but what happens when you try to run it on a server that has a different version of Python? It crashes. 2, it's not portable. To give this to a friend, you have to send them the code plus a long list of manual setup instructions. It's slow and error-prone. And 3, no isolation. What if another app on your machine needs a completely different version of the Flask library? You're in for a world of pain. So what's the solution to all of this? The container. Think of a container as a perfect sealed box. Inside this box, we place everything our app needs to run. As you can see in this little diagram here, we put our app.py file, the Flask library, and Python 3 itself, all bundled together inside that box. The works on my machine problem is solved. Forever. So how do we build this magical box? We use a blueprint, a recipe called a Dockerfile. This is our container blueprint. Let's walk through it line by line. First, from Python:3. This just tells it to start with a standard, clean Python 3 environment. Next, workdir/app. We're just setting the working directory inside the container. Simple. Run pip install Flask. This does exactly what you think. It installs our Flask dependency inside the container. Copy ... This copies our application code, in this case just our one app.py file, into the container. And finally, cmd, the command. This tells the container what to run when it starts up, which is python app.py. Okay, time for some action. You'll need to have Docker Desktop installed for this part. In your terminal, run this command: docker build -t joke app :1.0 space dot. What you just did is you created a standardized, portable package of your application. This package is called an image. Now, let's run it. Let's bring that image to life. Type docker run -p8080 :8080 joke app :1.0. And now for the payoff. Go back to your other terminal and test it again. Curl http ://localhost :8080. The output is the key insight. You'll see a joke. Why can't a bicycle stand on its own? It's too tired. But look at the second line. Served by A3F9C8B2D1E0. Some random string of letters and numbers. Look at that host name. Before, it was served by my laptop, your physical machine. After, it's served by that random string. This is definitive proof. Your app is no longer running directly on your machine. It's running inside its own completely isolated world.
So we have our portable container, a perfect sealed box. We did it. But here's the thing. If that box falls over, it stays on the floor. Our app is still fragile. This is where we stop just running software and we start managing it. This is a huge shift in thinking, and the single most important concept in Kubernetes, the idea that changes everything, is desired state. Listen closely, because this is the core idea. You don't tell Kubernetes how to do something, you just tell it what you want the world to look like, and it works tirelessly to make it a reality. Our first desired state is simple. We're going to tell Kubernetes, I want one copy of my joke app running. Always. Visually, it looks like this. As you can see in the diagram, we tell a manager what we want, and that manager makes sure our app instance is running. Simple as that. So what are these things, really? Let's talk about the abstractions, pods and deployments. The pod is the worker. It's the smallest unit of work in Kubernetes. Think of it as just a little wrapper around our joke app version 1.0 container that gives it a place to run. The deployment, now that's the manager. It's the boss. Its only job is to look at your instructions and make sure reality matches them. So you tell the deployment, I want one worker on the clock. What happens if that worker crashes? Well, the actual state is now 0 workers, but the desired state is still 1 worker. So what does the deployment do? It immediately hires a new one. It's that simple. So how do we write this instruction sheet for our manager? With our first YAML file. Okay, in your editor, create a new file called deployment.yalm. Now, I know what you're thinking. This looks intimidating. Don't worry about it. It's just a set of instructions, and we're going to walk through it step by step. Let's break this down. First, look at the line that says replicas :1. This is the core instruction. This is you telling the manager, I want one copy. That's it. That's the desired state. Next up, the template section. This is the blueprint for the worker. You're basically saying, hey manager, when you need a new pod, use the joke app :1.0 image that we built in the last chapter. And finally, the selector and labels. This is the really clever part. The deployment, the manager, selects pods with a matching name tag or label to manage. We're putting a label on our pods that says app:joke, and then we tell the manager to go find and manage any pods with that specific tag. It's how the boss keeps track of its employees. All right, action time. Let's hand this instruction sheet to Kubernetes. In your terminal, type kubectl apply-f deployment.yaml. You should see this, deployment.apps/joke-deployment created. That means Kubernetes read our file and is now working to make it a reality. Let's check on the worker. Run kubectl get pods. And there it is. Look at that beautiful output. You see a name, and then you see ready, 1 of 1, and status, running. That running status is proof. Our app is live inside the cluster. But now, for the aha moment, let's break it on purpose.
We are about to do something that would normally give a systems administrator a heart attack. We're going to kill our application. On purpose. First, copy the full name of your pod from that last command. You know, the one that starts with joke deployment and has all those random characters. Got it? Okay. Now, delete it. Type kubectl delete pod and then paste that full name. Now for the magic. Immediately run this command. kubectl get pods -w. That -w flag means watch. It's going to give us live updates. Watch your screen closely. This happens in seconds. You'll see your old pod, its status changes to terminating. But almost instantly, look, a new pod with a different random name appears. Its status goes from container creating to running in just a few seconds. Look at that. As the old pod was terminating, a brand new one was already being created. That is amazing. And here's the key. That wasn't you. That was the deployment. It saw the actual state. 0 pods had diverged from the desired state, 1 pod, and it took action immediately. This is the Kubernetes control loop in action. It's a simple, powerful algorithm running 24/7. Look at this table. When we started, the desired state was 1 pod. The actual state was 0 pods, so Kubernetes took the action to create 1 pod. Then things were stable. Desired was 1, actual was 1. Kubernetes did nothing. And then the crash. Desired was still 1, but actual dropped to 0. So what did it do? It immediately took the action to create 1 POD. This is self-healing. This is the power of desired state. We just witnessed Kubernetes do something amazing. Our joke app is now resilient. But that raises the next obvious question. It's running, it's safe, but how do I actually access it? Right now, our pod is in a private, isolated network. It's like having a new employee with no phone number and no email address. They're working, but nobody can reach them. We need to create a stable public entry point, a front door for our application. As you can see in this little diagram, the user right now just can't connect to the pod inside that private network in the cluster. The concrete problem is this. Pods are unreliable. Every pod gets its own internal IP address, but you should never rely on it. Why? 1, it's internal. You can't access it from your browser. It's not a public address. And 2, it's unstable. A new pod gets a new IP address. Remember when our last one crashed? The replacement got a totally different IP. You can't build a business on an address that changes every 5 minutes. We need a permanent, reliable address that never changes. So what's the abstraction? The service object. Now a service runs nothing. It's not another container. It doesn't run any of your code. Think of it as a virtual receptionist for your app. Its only job is to direct traffic. So how does the receptionist find the right pods? With labels and selectors. This is the really clever part. First, we put a label on our pods. It's like sticking a digital name tag on them that reads app:joke. Second, our service has a selector. It looks for any pod with that exact name tag. The service is the stable entry point. As you see in this diagram, the user visits the service. The service has a selector for app=joke, and it forwards the traffic right to our pod, which has the matching label. It's a perfect system. Okay, let's look at the concrete solution, the service.yaml file. We're creating a service of type node port to open a port on our machine. Let's walk through it. First, API version is v1, and the kind is, of course, service. We give it a name, joke service. Now, in the spec, we set the type to node port. This is what opens a port on your machine for easy access. Then, the most important part, the selector. It says app:joke. This is how the service finds the pods with the matching label we set up in the last chapter. And finally, the ports. The protocol is TCP. The service's own internal port, the receptionist's desk, will be port 80. And the target port, where the traffic should actually be sent on our pod, is 8080. All right, action time. Let's create the service. Let's apply it and create our front door. Type kubectl apply-f service.yaml, and you'll see the output, service/jokeservice created. Now, what's the address? Let's ask Kubernetes to describe the service. Run kubectl get service jokeservice dot. You'll see a table like this one. Now, the port in the 30,000 range will be different for you, but what I want you to focus on is that port S column. See that? 80:31234/TCP. This brings us to the aha moment. Let's demystify those three ports. A request from your browser goes on a three-step journey. Think of it like delivering a package to a secure apartment building. As you can see in this diagram, the journey has three steps. First, your browser goes to localhost at the node port. In this example, 31,234. That's the building's main entrance. From there, it's sent to the service port, port 80. This is like the internal mailroom. Finally, the mailroom directs the package to the final destination, the pod's target port, which is apartment 8080. This table breaks it down perfectly. The node port, like 31,234, is the public entrance. It's the port on your machine you access from your browser. Then there's the port, in our case, port 80. That's the reception desk, the service's own internal port. And finally, there's the target port, 8080. That's the final destination, the actual port your application container is listening on. Okay, let's do it. Action. Access the Joke app. Find your unique node port from the get service command and use it. I'm going to run curl http://localhost:31234. Remember to replace 31234 with your port number. And success! What kind of tree fits in your hand? A palm tree. And look, it even tells us which pod served the request. It works! Your request traveled from the node port to the service to the pod. The service found your pod using its label and forwarded the request to the correct target port. That is how you expose your application to the world. All right, we've come a long way. We have a self-healing application, and thanks to our service, we have a stable public address. This is a huge win. But we have a new problem. A good problem. Our Joke app is a viral sensation. Traffic is surging, and our single pod just can't keep up. It's like a popular coffee shop with only one barista. No matter how fast they work, they can only serve one customer at a time. The line gets longer, customers get frustrated. This is a bottleneck. So what do? To serve more customers, you don't make the one barista work harder. No, you hire more baristas. We need to do the same thing. We need to run multiple copies of our app and let our service spread the work among them. This is called load balancing. Our goal is simple. As you can see in this diagram, we want to go from one worker to 3. Our service will act as the manager, directing customers to the next available barista. So how do we do this? Do we copy-paste our YAML file and create new deployments? No. This is where the power of desired state comes back in a spectacular way. We don't tell Kubernetes how to add more pods. We just change the instruction sheet. We change our desired state from I want 1 pod to I want 3 pods. That's it. The deployment's control loop will instantly see the gap. The desired state is 3 pods. The actual state is 1 pod. So what does Kubernetes do? Its action is to create 2 new pods. And here's the best part. Our service will automatically detect these new pods. Why? Because they have the same app::joke label. It just works. I am not exaggerating. This is one of the most powerful features in all of Kubernetes, and it comes down to changing one single number. Okay, let's look at the file. Deployment.yaml. Find the replicas line, and we're going to change it from 1 to 3. You can see the code right here. Under spec, there's a line that says replicas:1. We're just going to change that to replicas:3. That is the entire change. Time for action. Let's apply our new desired state. In your terminal, type kubectl apply-f deployment.yaml. Now, notice the output. It says configured, not created. That's because Kubernetes is just updating an existing object.
Let's check the result. Did Kubernetes listen? Type kubectl get pods. And just like that, look at the output. We have 3 pods running, our original pod, and 2 brand new ones that Kubernetes spun up for us. Now, for the aha moment. Let's see our load balancing in action. Here comes the magic. Run the curl command against our single, stable service address 3 times in a row. Remember, use your own node port number. I'm going to run curl http://localhost:31234. Let's do it 3 times. Now look at the output on the screen. The first request says, "What has an eye but cannot see?" A needle. And notice it was served by pod ending in A, B, C, D, E. The second request, "Why can't a bicycle stand on its own?" It's too tired. Served by pod QRST1. And the third, "What gets wet while drying?" A towel. Served by UVWXY. Look at that. The host name is different every single time. This is undeniable visual proof of load balancing. We hit the same address, but the service automatically spread the requests across all 3 of our pods. Think about what we just did. With a 1-line change, we scaled our application to handle a massive increase in traffic. A real-world site uses this exact same workflow to go from 50 servers to 500 for a Black Friday sale. The only thing that changes is the number after replicas. The principle is identical.
Our joke app is now a beast. Let's recap. It's self-healing, it's publicly accessible, and it can scale to handle a ton of traffic. But we have one last critical problem to solve. The jokes are getting old. We need to update our application with new code. Now, the challenge here is immense. How do you update the application without any downtime? You can't just turn it off, deploy the new version, and turn it back on. That's not how the real world works. We need to change the tires on a car while it's driving down the highway. It sounds impossible. It really does. But with Kubernetes, it's not only possible, it's the default behavior. This is the final payoff. We're going to perform a zero-downtime rolling update. So what does that look like? The process looks exactly like this. If you look at this diagram, you can see the user on the left just hitting refresh over and over. As they do that, Kubernetes starts creating new pods with the new version of our code. It waits for one to be ready, then starts sending traffic to it. Only then does it delete one of the old pods. It repeats this dance. Add a new one, remove an old one, until the entire application is updated. And the user? They never see a single error. The abstraction behind this magic is called the rolling update strategy. This is the default update strategy for a Kubernetes deployment, and it follows a very careful, methodical algorithm. First, it starts with the new. It creates one new pod with our v2.0 code. Second, it waits for readiness. It waits until that new pod is healthy and ready to accept traffic. Third, it removes the old. Only after the new pod is ready does it terminate one old pod. And finally, it repeats. It continues this cycle until all pods are running the new v2.0 version. It's safe, it's reliable, and it guarantees no downtime. So, let's talk about the concrete solution. It's a simple 4-step process. Let's do it. Step 1. Update the application code. We'll go into our app.py file, add some new jokes, and most importantly, we're going to add a v2 marker to the output. You can see here we added a couple of new jokes, and then in the return statement, we add that little v2 string. This is going to be our visual proof that the update is working. Step 2. Build a new container image. Now we package this new code into a new image with a new version tag. We'll run docker build-t joke-app:2.0 space dot. Simple as that. Step 3. Update the deployment's desired state. We're going back to our instruction sheet, deployment.yaml, to tell Kubernetes we now want version 2.0. Look at the change here. It's so small. Under spec, containers, we find the image line. We're just changing the tag from joke-app:1.0 to joke-app:2.0. That's it. We're just updating our desired state. Step 4. Apply the rolling update. Let's tell Kubernetes to make it so. We'll run kubectl apply-f deployment.yaml. The output says deployment.apps/joke-deployment configured. The update has now begun. And now for the aha moment. Let's see the live update. Get ready to open two terminals side by side. This is where it all comes together. On your first terminal, the admin's view, run this command and just watch it. kubectl rollout status deployment/joke-deployment. Don't do anything else, just let it sit there. Now, in your second terminal, the user's view, while the rollout is happening, you're going to spam this command. curl http://localhost:31234. Hit the up arrow, hit enter. Over and over and over. This is the magic of Kubernetes. In Terminal 1, the admin view, you'll see messages like, waiting for rollout to finish. 2 out of 3 new replicas have been updated. And then finally, deployment, joke deployment successfully rolled out. But in Terminal 2, the user's view, you'll see the output switching in real time. 1 second you'll get an old v1 joke, like, what gets wet while drying, a towel, served by an old pod. And the very next second, why did the math book look sad? It had too many problems, with our v2 marker, served by a new pod. This is it. This is proof of a zero-downtime deployment. For a brief period, both v1 and v2 of your application were running at the same time, and the service was load balancing traffic across both of them. The user never saw an error. The service was never interrupted. The update is complete. Now and forevermore, if you run that curl command, you will only see responses with the v2 marker. You just changed the tires on a moving car. Let's take a step back for a moment and really appreciate what we accomplished. We started with a single Python file on a laptop, a fragile little script, and we ended with a resilient, scalable, and updatable service running on Kubernetes. The most incredible part? We used the exact same workflow to solve every single problem we encountered. Think about it. We faced 5 different challenges, and we solved every single one with the same 2 simple steps. Number 1, describe what we want in a YAML file, and number 2, run kubectl apply. Let's recap this journey. We had 5 challenges, and we solved them all with this core loop. First, package. We solved the classic works on my machine problem by creating a standard container image using a Dockerfile. Second, define. We solved resilience by defining our desired state in a deployment, which gave us a self-healing pod. Third, expose. We solved accessibility by creating a service to act as a stable front door, using labels and selectors to find our app. Fourth, scale. We solved the traffic problem by changing one single number, replicas:3, in our deployment. And fifth, update. We solved updates by changing the IMAGE tag, triggering a perfect zero-downtime rolling update. Do you see the pattern here? Create, heal, scale, and update. We never told Kubernetes how to do these things. Let me repeat that. We never told Kubernetes how to do these things. All we ever did was change our definition of the desired state. The command was always kubectl apply. The only thing that ever changed was the instruction sheet we gave it. This declarative model is the simple, powerful, and truly revolutionary idea at the heart of Kubernetes. And I want to be crystal clear about something. This workflow you just learned, this isn't a beginner workflow. This isn't a toy example. This is the workflow. The exact same process you used for this little joke app, engineers at Google, Netflix, and Spotify use it to manage massive globe-spanning services. The only difference is that their YAML files are a bit more complex, and the number after replicas colon might be 5,000 instead of 3. You didn't just learn some concepts today, you mastered the fundamental operational model for building and running modern software.